Hi everyone. Today we are going to discuss one important nuance that we have never discussed in deep learning talks in the past 43 episodes. We have discussed the idea of attention a lot, right? But we have never discussed the idea of cross attention, right? So let's look at where does it come from and where is it lying in our architecture, which is worth reading. So one of the architecture that we keep on emphasizing is the encoder-decoder architecture. This encoder-decoder architecture is mentioned in the paper known as Attention is All You Need, right? So we call it a billion-dollar paper, right? So what exactly is the architecture? We can have a look here. We can see that we have a lot of input text coming in. Then we convert token embeddings or we generate token embeddings and positional embeddings. Then we linearly do an addition operation. This acts as the input for encoder stack. So we have an encoder stack and then we have a decoder stack. Then we have some linear layers, right? And then we have our predicted token. Supposedly, so this paper is emphasizing the machine-to-machine translation, sequence-to-sequence translation, word-to-word translation. So, for example, let's say we are doing "Hello World," right? So, "Hello World" is English, and we are doing English to French, right? Because "Bonjour" is so. This particular stack is helping us do that particular translation. Now we have an encoder stack and we have a decoder stack. We have discussed a lot about in detail what exactly is multi-headed self-attention. We have discussed in detail about adding the residual and layer normalization, the scaling and shifting vectors in layer normalization, and why do we need residual. We've discussed the importance of feed-forward neural network, right? We have discussed, okay, again, this is the same. So we have six layers, this particular stack each. So six is a hype parameter here, right? So the user decides how many layers do I want. In this paper, they have taken six layers of this particular stack and six layers of this decoder stack. In decoder stack, we can see that we have masked multi-head self-attention. So I think we've also discussed the idea of causal masking, which is also very relevant and prevalent in the GPT family and in all decoder-only stack. So if we try to recall, the encoder-only stack, which we have discussed is BERT, the decoder-only stack that we have discussed, and we keep on referring back to, is the GPT family stack, right? So the GPT family uses this particular stack, only this, without an encoder to generate the next token. Now, masked multi-headed self-attention is what we have already discussed. This is something which is very much new, right? So, first thing is what exactly, if we try to decode, so we will do a session where we will deep dive into the whole research paper end to end. But for now, let's try to understand a couple of things to get to cross attention before first understand for people who might be confused, why do we have six layers? So in the original paper, which is attention is all you need, n is equal to 6 is nothing but a hyperparameter. When we say that encoder has six layers, we simply mean input is processed through these six identical structures, through these six identical layers, and it is always in a serial chain, right? The encoder stack is taking the output of the previous layer, right? Each particular stack is taking the output of the previous layer. By the time we reach the sixth layer, the initial token embeddings have been refined six times. So this is the idea of incorporating it in an increasingly six amount of encoder stack. What about the decoder stack? Similarly, as to what we had in encoder stack, we have a same idea that we will keep six layers for decoder stack. And each layer in the decoder stack is heavier than an encoder layer because it contains three subcomponents instead of two. There we only had two subcomponents, which is the masked, which is multi-headed self-attention without masking and feed-forward neural network. Here we have multi-headed self-attention, but with causal masking, and we have cross-attention. Then we have feed-forward neural network, and obviously, after every particular sub-layer, we keep on doing residual and layer normalization function, right? Now, to bridge the gap between an encoder and a decoder, we have something known as cross attention. Now, why do we call it cross attention? We call it cross attention because it takes the input or the source of the attention's input is the encoder, right? We can say that the information is flowing from top to bottom, encoder to decoder, right? What about this attention? What about self-attention is taking its input as this particular vector, right? So the size of cross-attention and self-attention might be same, but the source is completely different, right? So this is the main idea. So query is coming from the decoder. Let me just show you now what exactly are the nuances of cross attention. As we can see here, let's pay a little attention. So we know every attention matrix is going to have its own key, query, and value. right? So the query comes from the decoder. The key, which is K, comes from the encoder. And the value is also coming from the encoder. So the decoder is currently trying to generate the next word in the target language. Let's say the target language for this paper is French, right? So query is basically saying, I am currently at position I in the French sentence. What information should I be looking for? Key from encoder says, here is the map of all the concepts in English source sentences, right? Whereas value says, and here are the actual semantic context or semantic content of these particular concepts, right? So query is coming from decoder, and key and value both are coming from encoder, which is from the above stack. So if we look at them from top to bottom, key and value are coming from the above stack and queries coming from the decoder itself. So the only idea in cross attention is that they are paying attention to what is coming from the encoder, right? And the source of information has changed. For the decoder only stack or for self attention, we did not have, this cross stack exchange of information. They simply looked at the embeddings. Now, embedding vector was a combination of token embeddings and positional embeddings, right? So it looked at that combination. That's it. But when it comes to cross attention is looking at the encoder stack, right? It's taking some information from the encoder, it's having some of information of its own, right? Now, why are we doing this, right? So why do we need to do this particular thing? So if we don't do this, if we don't have something like a cross attention, the decoder would be blind to the source sentence. The decoder might not be able to see the source sentence. It would essentially become like a GPT family transformer where it is essentially generating the next token and hallucinating on the text based on what it has already generated with no reference to the input, that you want to translate or that you want to summarize, right? So the use case here for this particular stack is not only generation. The use case here is to translate, is to maybe summarize, right? So we need the relevant encoder positions to decide what to generate next. So this is the main idea. Before we had this particular stack, which is cross attention, we had some other alternatives in the sequence to sequence models, which is concatenation, which didn't work out well. There's no point looking at them. So the only thing is that the formula for attention remains the same. There is no masking, and decoder is trying to attend to all encoder positions. Only the source of information has changed, and the narrative behind changing the source of information is that if we let go of cross attention, the decoder will not be able to interpret the source sentence, and it would essentially become or behave like a GPT, and it would try to just simulate or hallucinate the text, the new text based on what it has generated in the past, right? So this is what we don't want. That's why we have something like cross attention. Thank you.